linear combination and spanning sets. So here are a few definitions or things to remember. Basis vectors or spanning set. All vectors can be written uniquely in terms of unit vectors I and j in 2 dimensions or I, j and k in 3 dimensions. Vectors such as these are termed as basis vectors. We say that they form a spanning set of vectors. So what we are trying to say here is that if we are doing 2D or R2, in that case I and j forms a spanning set, means any vector in our coordinate plane can be represented or written as a linear combination of I and j vectors. For example, if we have a point here, right, and the point is a comma b, in that case it really means that this has an x component of a and y component of b, and therefore we can write this point as ai plus bj, where a and b are real numbers. So that becomes a linear combination. Do you see that? That's what we're trying to say. Any vector in R2 can be written in this fashion. Since it can be written in this fashion, we say that a and b, since it can be written in this fashion, we say that unit vectors I and j forms a set which spans in R2. Similarly, in R3, I, j and k forms a spanning set. So any vector in R3 can be written as linear combination of I, j and k vector, right? Another way of saying the same thing is that I and j are basis vectors for R2 and I, j, k are basis vectors for R3. So now in this definition, our key word here is uniquely. All vectors can be written uniquely in terms of unit vector I and j in 2 dimensions or I, j and k in 3 dimensions. Now if there is a vector AB here, then we can only write it as AI plus BJ, not anything else. Can you prove that? So that is the next question. Show that the representation vector u equals to AI plus BJ is unique. So that is a part of question which we'll try to understand here. And we'll try to prove it in a different way. We say, well, let it not be unique, right? In that case, there is a different A and there's a different B, which could be written here to get the vector u, right? So we say, let u be equals to A1i plus B1j and also equal to A2i plus B2j. Okay, since we say it is not unique, let us assume that it is not unique. Then there are more than one set of values for a and b. So let us assume these are the 2 set of values. So we are providing a very general solution. But since both represent the vector u, they should be equal. And therefore we can write a1i plus b1j is equals to a2i plus b2j. And let's reorganize it. So if we rearrange it, we get a1 minus a2i equals to b2 minus b1j, correct? Where I and j are unit vectors. Now, if you see this statement, it means what? Scalar a1 and a2 are real numbers. b2, b1 are also real numbers. So their difference is also real. So we are trying to say that scalar multiple of I is equal to scalar multiple of j. That's not possible since I and j are orthogonal vectors. They are in opposite direction. So they cannot be parallel. So this statement says that they are parallel since we are equating them as a scalar multiple, which is not possible, correct? So this statement is not true, right? Since I and j are not parallel, right? They are orthogonal. Above statement is false. Therefore, our assumption is wrong, correct? And so we can say that u can be uniquely represented as ai plus bj, right? And this is only possible, this equation is only possible if a1 is equals to a2, or and rather b2 is equals to b1, right? Otherwise it is not possible. For non-zero a1 minus a2, non-zero a2 minus b1, it is not possible, since I and j are not parallel, correct? So it is possible if and only if a1 equals to a2 and b1 equals to b2, then this equation is true, right? Only then. Above equation is true, right? So we have proved that a1, a2 are actually the same points. b1 and b2 are actually the same values, correct? So they are unique values. We cannot have more than one value in this relation. I hope you appreciate that part. Thank you.